Good afternoon. So, in the last class we talked about several indole syntheses. This is the last class on indole synthesis, not last class of the heterocyclic chemistry. Okay. So, last time we talked about what? 3 different methods. One was Fischer indole synthesis, other was no. What is the second one? Bartoli synthesis, third one Nenith-Jetsku. Okay. And what I said, on the basis of the starting material you should remember, because that is the way, it is pretty easy. So for example, when I say Fischer indole means it starts with hydrogen derivatives, okay. And then next thing what you should remember, the most common intermediates. For example, Fischer indole synthesis, one of the most common intermediates could be vinyl hydrazine. So then you can, that means if you know the intermediates, you can just formulate your own synthesis, and on the basis of that, and there are so many variants. One of the variants is Japp-Klingman method. So, where you can make hydrogen by a different way. Second variant could be Moody's one, Christopher Moody's one. He has made this Bock protected hydrogen derivative. So, likewise there are many more. Buchwald also has produced a variant. So, similarly Bartoli is pretty easy to remember. It requires nitrobenzenes, nitroarenes and Grignard, vinyl Grignard. No, not any kind of Grignard, again a vinyl Grignard, that was vinyl hydrazine and vinyl Grignard. And third category was on basis of this Nenith-Jetsku. Nenith-Jetsku requires the benzoquinones and enamino-ketones. So, this is how you have to remember. Okay. So, there are many ways to, there are many more methods, and I think we will talk about today one very important indole synthesis, which is not really listed in the books, most of the books, very few books would enlist, but it is a, as you will go and see that it is a pretty powerful reaction, very powerful reaction. There are very little problems, of course, and so this afternoon we will talk about the mainly 3. So, the one that is called Hemetsberger, this is one we will talk about, and then second one probably we will talk about how do we say, okay, let us say cross dehydrogenative coupling, and third one that probably we will talk about is again a very powerful, this is called Larock hetero annulation, which is again Larock, one can say indole synthesis by Larock's method. And the fourth one, that it depends, if the time permits we will talk about again. This should be there is no name, but I think I will how is that, I will write Nockel, not really Nockel, but Nockel type synthesis. No, is okay. Now, as we go on, again I said you have to identify the starting material, then the little bit of mechanism, then the applications. Okay. And so, let us begin with this Hemetsberger. So, what does it do? Actually, it requires beta azidostyrene. So, that means if you write this structure this way, what you will see here, the adjacent position is alpha. So, this is beta. So, beta azidostyrene, and if you heat it, not very at high temperature, just at less than 200 degree centigrade. So, what you are likely to get? You are likely to get a product which is nothing but in one, that means sort of like a neutral conditions, you can get to the product here, this is Indole, that is it. So, right, and what is the mechanism? The mechanism is that it is suggested it loses nitrogen. So, it loses nitrogen, and of course, once it loses the azide loses nitrogen, that means what you will be getting? You will be getting this nitrine intermediate. So, like carbene and nitrine, and of course, one can nitrine, right, and but then what happens? Then the nitrine, what are the other possible reactions with the nitrine? Nitrine insertion. Yes, well, I think the very first thing that one should talk about is the isomerizations, because isomerization requires only very little change in this skeleton. So, in fact, this is suggested and it has been verified, as you will see later, that it gives you a molecule of this kind. So, which is nothing but azirine. So, nothing but azirine. So, azirine derivative we get, okay. And so then of course, if you recall, this azirine derivative has a propensity to undergo rearrangement. What kind of rearrangement? Pretty much like that, not exactly though. So that means that can undergo this one, okay. And so then this is the suggested mechanism, and probably it is accepted. Only you can also question why not directly nitrine undergoes insertion to these carbon hydrogen bond of these benzene ring systems. All that possibility is ruled out, as we will go and see the next example. We will see there are quite a few variants of these, where you can start from azirine and you can go on making this indole, and simply because azirines are very readily available from simple starting material like oxime, you can make azirines pretty easily without much problem, okay. And so let us begin with an example, and like say if you are supposed to make an indole derivative, for example, where you will have indole and 2 position you will have a hydroxymethyl group and bromo here, and then this benzyl protecting group and then OME. That means a heavily substituted indole derivative. We have 1, 2, 3, 4 substitute. So, how do you make it? So, how do you make it? Any guess? That means if you look at the top one would find out if one would make a vinyl kind of azide or azidostyrene you can make, right. So, what kind of azidostyrene we will take? We will not take, and that means if you just do a little bit of the disconnections, you will find that you need a azidostyrene with a CH2OH functional group. But at the same time you have to think about whether that is really required or not. If you want to know the methods of how to make the azidostyrene, you will see that it is a little difficult to make, number one. Number two, if you begin with a CH2OH group during the decomposition of the azide, there is a likelihood that this it will undergo nitrine insertion on the other side, instead of being formed instead of giving this azirine intermediates, okay. So, in this case you had in the top one you had an ester group. So, there was no possibility of insertion on the right hand side, on the ester side, but if you think of a CH2OH here, you can think of an insertion reactions with the nitrine. So, essentially in this case what has been done, this has been obtained from the corresponding ester derivative, and this aldehyde. So, take the aldehyde here and then the azidoester, in this case this azidoester is pretty easy to make. So, take then sodium ethoxide or methoxide, then typically what you will find? You will find just like in aldol type of condensation. So, you will get this azidoesters, and then what? Just simply again heat in xylene solution. So, you get this corresponding, you will get the corresponding indole, that is this one without any much problem, and so you will have this methyl ester here, and of course, once you know that this methyl ester is there, then it is pretty easy to reduce this to corresponding alcohol. Okay. So, this is pretty straightforward. Then what is the problem then? There is just only a small limitations is there. Anybody who knows about the limitations of the azides? What could be the limitations? You see here, just the preparation is pretty easy. If you have azido acetate, you can do sort of an aldol type, you can get the vinyl azide, that is all these problems are pretty easy. But this reaction is little tricky, that is it. But that is not a serious problem. The problem is that large scale production, because it is known that in most cases these azido compounds are explosives, azides are explosives. So, whenever you do reactions with azides, you have to be very careful. You never know when it explodes. In small quantity, of course, I mean we have been doing work on this, but so far we have not come across any problem, but it is reported that one should be pretty careful about this. But merits of this method is that you do not have to make azide though, that means you can bypass it, because we know the reaction mechanism. What was the reaction mechanism? Azides when decomposes, it forms the azidine. So, azidine can be made alternatively by at least I know there are two different very convenient methods. For example, the one way to make is to make an oxime. So, if you begin with an oxime here, like oxime, all of us know how to make oxime, right? Corresponding ketone and hydroxylamine hydrochloride, it is a very good reaction, and it is a standard reaction for derivatizing ketone, so there is no problem. Then you do Neber reaction. What is Neber reaction? Neber reaction is nothing but the first step you make this into methyl derivative, that means methane sulfonyl chloride and triethylamine. So, I think I do not have to write the intermediate, it converts the the OH group to OMS, right. So, this basically OH is converted to OMS, and then second step, if you do DBU, so what you will be getting? You will be getting the corresponding azidine, sorry. So, will be corresponding in getting 1, 2, okay, nitrogen here double bond, and this R1 and R2. So, you get this azidine. Of course, that means you can bypass the demerits of the Hemetsberger procedure. Okay. Alternatively, there is another way of looking at one just take, let us say you have something like this R1 and let us say electron withdrawing withdrawing group and NH2. So, how do you make it? It is an enamino ester. In the last class we talked about it, right. These enamino esters are required in the reaction of Dehydrogenative reaction. So, it is easy to make. So, if beta keto ester kind of things, then ammonia that would give this. So, the same starting material if it is reacted with a reagent which is written as this one, phenyl iodinium diacetate. phenyl iodinium diacetyl. It is a very useful reagent, and for last maybe what 10 years we have been continuously using this reagent, and this belongs to a class of reagent known as, guess, very good, hypervalent iodine reagent. There are plenty of reagents based on this. Why hypervalent? Normally iodine is considered to be monovalent, in this case divalent, there are pentavalents also, all of you know, but most cases the trivalent iodines are pretty powerful oxidizing agents and mild and selective. So, depending on the situation you can make use of it. There are many uses, we will see one more use also towards the end of the lecture. Okay. Plus it is innocent, the byproduct is iodobenzene. So, that means it does not cause any decomposition of the products or the starting materials. So, that way this is pretty easy, but it is a nice oxidizing agent, and so what you get once again, what you get is basically this you will get this azidine, substituted azidine here and electron withdrawing group here. Okay. So, that means you can have all kinds of the azidines. Okay. Now what you will find that azidines again you know can be converted to indole, you have already seen before, by simply heating it, but you do not have to heat at high temperature. People have been using different catalysts now. For example, the one recently used okay, is palladium chloride, and then there is a acetonitrile complex, right. Those who are working with palladium complex, you will see it is a very stable complex with 2 acetonitrile, So, well sorry, in this case it is a benzonitrile. It forms a nice complex, and this complex is pretty soluble also in organic solvent. So, with this complex you can decompose this azidine directly to the aniline, indole. Okay. So, similarly there are or you can use, I think the one that is used to generate carbene from diazo compound. What is this? Dirhodium what? Dirhodium tetraacetate. This is a very dirhodium tetraacetate. This is very nice again a complex. Is basically what it does, it lowers the temperature of the decomposition of these azidines or azides, and it generates nitrines and carbenes milder conditions. And then the latest one, I think latest one is pretty interesting, it has been published in 2010, and what you add is nothing but ferrous chloride, and that too with only 5%. So, you see here the trend here, that was the palladium expensive, the rhodium little I mean almost equally expensive, but ferrous chloride is pretty cheap. Anyway, you will walk into this lab and find out the ferrous chloride, and at low temperature, lower than just around 180 degrees centigrade, you can decompose and get the indole. Okay. That means this is a very powerful method with regard to the starting material. You can either use azides or you can use azidines, and that azidines can be obtained from the ketones or the oxenes, and they for their decompositions or for the rearrangements you have many options, different kinds of the catalysts and these things. Okay. And then so what next? This other, that means again going back to the little bit to the last class. So, we had only there are two different kinds of methods, right, general methods. One is monosubstituted benzene, other is the disubstituted benzene. The third and fourth categories where you can make the benzene derivative is not really very popular. Okay. So, and in this one you can see here this is a monosubstituted ones, okay. There are other ways also to look at. For example, if you take enamine kind of thing, here if you take a ketone straight away make this enamine, and so what you can guess, how do you make indole from here. So, what is the reagent would you like to use? if you just take the atom balancing, if you do the little bit of atom counting, what you will find it actually removes 2 of these indicated hydrogens. So, that is the reason this is known as dehydrogenative. Dehydrogenative, this is a word very recently used, dehydrogenative coupling, dehydrogenative coupling. That means minus 2 hydrogen. So, you end up with the corresponding Indole derivative. So, in principle it looks pretty good, right, and so easy, and enamine formation you take from the ketones and do a little bit of the isomerations, and then you get this enamine done. Well, but of course, you have only limited choice, but I cannot say so, but because by now it is known that there are more than 8 different catalytic systems are found to be useful. Okay. And most of them are published in good journals, and but basically what you need, you need either palladium based catalyst or copper based catalyst. Palladium based or copper based catalyst. I think all of you can agree that okay, palladium has a tendency to undergo C palladation reaction. Okay. Means like say any palladium chemistry reactions, what do you do? Let us say first thing you have learned in last year that all the cross coupling reactions would involve palladium. Why? Because the palladium undergo first insertion, okay, insertion between the carbon halogen bond, and then it goes on for reaction with another carbon bond, carbon to form carbon palladium linkages. Okay. So, in this case I think I will give you the possible catalyst, then I will tell you how to see the mechanism. Okay, let us say all are very similar, but and only they differ little in their composition. For example, the very first one, the popular one is palladium acetate, and this of course this is expensive. So, you have to use catalytic amount, and the stoichiometric catalyst could be then stoichiometric catalyst could be copper, because copper acetate is cheaper, and all of us know you need also a base, because eventually acetic acid etc. would come out. So, in this case the base that is used is potassium carbonate. This is one. Okay. Let us say second one you will see once again it is little better in the sense that you use palladium, once again catalytic amount, then cupric acetate is again the catalytic amount, then what is the stoichiometric oxidant or what we call terminal oxidant is oxygen itself. So, that means this second one is a better one. Okay. Third one is little different. And ferric chloride once again it is a catalytic amount, then cupric acetate. So, all possible combinations are there, then combination and then with cupric chloride, and that has to be has to have a base here, right. So, fourth one, I mean once again the previous one was palladium acetate, cupric acetate, oxygen. You can skip cupric acetate, all different combinations. Basically, you have to do little bit of the trial and error, and the one that is little uncommon here is a cupric iodide, the cuprous iodide, and fen, right. Fen all of you know, and in this case lithium carbonate, because it is little more soluble in organic solvents. So, what is fen? Fen what is that, but not 910, it is not 910, I suppose it is 110, fen has to be 110, right, not 910. Or orthophenolphthalein, that is I think okay fine, I think we will take it orthophenolphthalein. So, like this I think there are many more combinations. I think I will stop here, and of course, the one more very popular one is this one, this phenyl adenine diacetate. This is also has been used, and that too at a pretty low temperature at 60 degree centigrade. So, you have all kinds of the options, and mechanistically, I mean, and obviously mechanistically, if you look at the mechanism. So, what is the first step? The first step would involve palladation of a that means hydrogen here let us say you have palladium acetate, right, and all of us know how to shift the arrows from enamine. So, it goes to palladium, and so what you will see then further rearrangement. So, what we will be getting? You will be getting R1 R2, and here would be palladium acetate, right, all of us know. And I mean I just skipped the second step, that is the loss of hydrogen from the position swap hydrogen palladium is attached, right, just like aromatic electrophilic substitution reactions. So, hydrogen is lost, and then you get to this. So, palladium is now incorporated at the beta position with respect to the nitrogen, and what is next? These are all the standard protocol. What is expected now? What is next step? So, these are all typical organometallic mechanism. I mean there could be many more. The organometallic chemist would do all kinds of things, then pi complex, this thing, insertion, substitution, all these things, but organic chemist skips all those steps. Basically we just very quickly go to the final product. So, what is the next step? Next step is the insertion of palladium between carbon and hydrogen. I mean there are so many carbon and hydrogen, of course, the one that is aromatic one CH2. So, what you will find so something like this would form. This is R1 R2 and hydrogen and this, right. So, and then so the messages are then of course acetic acid comes out, right, acetic acid comes out, and then you have all kinds of the ligands here, and by now all of you know what is the next step? Reductive elimination. So, reductive elimination, and that means it will go like this and this. So, once you have reductive elimination of palladium 0. So, what do you get? You will get the product palladium 0, and then there the palladium has to be recycled. Recycled means has to be converted into divalent palladium. So, you need an oxidizing agent. What is the oxidizing agent? As you will see on the list, in one case it is cupric acetate, other case cupric acetate oxygen, and oxygen will will be activated to hydrogen peroxide, that oxidizes this palladium to palladium 0. So, all kinds of techniques are there, then ferric chloride, different kinds of the oxidizing agent. But in certain cases the reactions are bad, some reactions are very good depending on the situation, and you have to be little expert in finding out the optimum conditions. But in organic chemistry often we do what we do, we just keep on optimizing different things without knowing little bit of these things, right. Okay. So, but any case, but this method of unfortunately, for example, I will not tell you the exact problem. Long back we had a similar problem, we could not solve the problem, okay, and we could not solve the problem. Maybe in a few months time we will again take up the problem, exactly this very similar problem, only thing that R1 R2 was a member of a cycle, R1 R2 were member of a cycle. So, we could not connect them, but someone, in fact many of you know, he is pretty well known heterocyclic chemist, or right, Noel Carr, right, Noel Carr, he came here he has done this thing pretty easily without much problem. He has used cupric acetate and phenyl adenine acetate and got the carbonyl derivative without much problem. That means, in this case the other side also is a cycle, but he could get to this carbonyl derivative without. Okay. A few years ago, I mean, one also could one could also convert this just simply with iodine. Iodine is an oxidizing agent for all practical purposes, because it gets converted to iodide. So, if you just mix them together in a high temperature, it can give you the carbazole. But in principle there are many methods available, and what you will see here, I will give you one more example. It is again starting from monosubstituted one, but in this case this enamine is little different though. So, again it is an enamine though, enamine. Now, nitrogen is not linked to the aromatic ring system. So, you have a hydrogen here, that means circled hydrogen, this circled hydrogen, and there are two different kinds of hydrogen. So, if you have a proper oxidizing agent, and it should undergo dehydrogenative cross coupling, or we call cross dehydrogenative coupling. So, once again the combination is palladium acetate, cupric acetate, and this is 10 mole percent. 10 mole percent means catalytic, and this is 1 equivalent cupric acetate, and of course, without saying one can write the corresponding indole derivative. So, that means this example will tell you as a pretty useful reaction, the useful way of looking at the. Now, next one, this has been very popular these days. This is known as Larock hetero annulation, right? Hetero annulation, and what is the meaning of annulation? Formation of a new ring with formation of minimum two bonds, with minimum two new bonds. Okay. Formation of a new ring via formation of minimum two bonds. Okay. In this case, you are incorporating one heteroatom into the new ring. So, that is the reason it is known as heteroatom. And what is the starting metal? In this case, it is the previous one was sort of like intramolecular reactions, but in this case the Larock annulation of the name itself says that actually it should be intermolecular reaction. Normally annulations are intermolecular reactions, that means you have to have two different components, okay, two different components, and in this case one of the component is, let us say like this, that is alkynes. One of the component is alkyne, and then other component is now for a change, it is now a disubstituted benzene derivative. That means iodoacetanilide, let us say iodoaniline kind of iodoanilines. So, one class is iodoanilines, other kind is alkynes. By the way, these alkynes are known as or classified as internal alkyne, right. It is not a terminal alkyne. Terminal alkyne means hydrogen is free. Okay. So, internal alkynes, and what is again the catalyst is say palladium based catalyst. So, palladium based catalyst, and often a little bit of sodium chloride, lithium chloride is used, many of you know, because it is easier to substitute ligand with a chlorine at the palladium. Okay. And advantage that you get aniline derivative. So, disubstituted aniline derivative, 2-3 disubstituted aniline derivative in one single pot, fine. Now, so that means if you have a symmetrical alkyne, there is no problem, but if you have, let us say if you have two different group, one is large, of course the other is a smaller one, then you will have different problems. the 2 position could be with larger, other one could be smaller. So, there are you have a possibility of regioisomeric for regioisomer formation. Okay. Fortunately, this method is very regioselective, mean it gives only one isomer exclusively, and if you know a little bit of the reaction mechanism, you can predict which one would be which one would form. That means, whether larger would be at the 2 position or 3 position. Okay. But any case, that is the reason why this method has been become very popular, because it is one part regioselective, it can tolerate it can, or rather I mean the substitution tolerance are very high, tolerance is okay. So, guess which one between the 2 R groups, which one would be the larger one? See, often you see when you go to this typical electrophilic nucleophilic substitution reaction etc., you will follow a mechanism. But if you want to just if you want to change the orientation etc., then you go to the organometallic compounds. So, organometallic compounds gives a sort of counter thermodynamic product. For example, many of you know, if you have an internal double bond, you can shift it to the terminus of an alkene by using an organometallic compound, right. What is that? There are methods. You have an internal olefin, you want to shift it to the terminus of the chain, carbon chain. You do hydroboration. You do hydroboration with a bulky group, then keep on hitting because of the bulk, it will go to the end. Then you use one more alkene, where this boron would be transferred to the second alkene. So, like this, you know. So, similarly, this most of the organometallic reactions are sensitive to steric effect. Because of that, this R larger would be in a particular position and giving rise to the particular regioisomer. Okay. I will give you the answer, let us say if you can make out, and in almost always the larger group would end up in the position 2. So, obviously, the other option is this is the smaller one. Okay. And mechanistically okay, should I write? Mechanistically one can quickly think about that palladium has a job to undergo oxidative addition, right. So, if you have palladium 0, you will undergo oxidative addition. Then what? Palladium, because of the iodine here is electrophilic in nature, right. So, one would expect that the polar character would dictate this orientation of the acetylene, but in this case because it is a metal templated reaction. So, eventually this larger group should be away from the thing, and it will undergo insertions the way here larger here and the R here is a smaller one. Okay. So, I mean you can say first it forms the complex, and then this is smaller one, and here you have a palladium etc., are larger, then NH acetate, and then of course, the palladium undergoes reductive eliminations. So, reductive elimination. Okay. So, so this is how, that means basically during this insertion it is oriented in such a manner that actually the smaller one would be linked to the benzene ring system. Okay. So, that means it is a powerful reaction, it is one part reaction, starting metals are very simple alkynes. Okay. All this orthoaniline, orthoiodoaniline can be easily made, if you have proper substitution, you can just simply adding iodine to the aniline, you can get the corresponding iodo compound, because anilines are pretty activated. I will just give you one example that will tell you this importance of this reaction. If you, and it can accommodate all kinds of the substituents here, like you have aniline, oxygen here, and then this is a chiral auxiliary. I do not know whether you know or not. This is a chiral auxiliary where you will have this ethoxy on both the sides. Then you have isopropyl group here and TES. Let us say this is a chiral auxiliary. Reaction conditions, palladium acetate, lithium chloride, then sodium carbonate and DMF 100 degree centigrade, 100 degree centigrade. So, both the substrates satisfy the requirements. One is iodoaniline, then other one is an alkyne, internal alkyne, and now you have to decide this see here a triethyl silyl group, and on the other end of this alkyne you have CH2. So, between the two, which one is larger? I think all of us would agree silicon, right. Silicon is heavily substituted, so it is a larger group, and these other auxiliary, which is known as, actually is a pretty famous one, Skolkoff. This is called Skolkoff auxiliary. It's a must auxiliary, it can produce amino acid, actually it can produce amino acid. Okay. And it is obtained from, if you look at this substrate here, this portion comes from valine, the other portion comes from the glycine. Okay. And and this imine portion remains unaffected, silicon moiety remains unaffected, and in one part what you will be getting? You will be getting this aniline, sorry, indole derivative here, and this one is the terminal alkyne portion, and this is triethyl silyl portion, and then you have this group here, then the nitrogen, both the nitrogens are with respect to each other in the 1 and 4 positions. Then you have this isopropyl side chain and this ethyl side chain, ethoxy side chains, that is it. And it could have been the otherwise, but as I said already that this larger group would be attached to the C2 position. So, you will have a nice this one, this linkage, and what next? And if you just treat it with 2 normal HCl in ethanol, and what you will find, of course, the indole ring is pretty stable. There are three things which take place here. Three things actually hydrolysis. So, hydrolysis would give you this amino group here, ester here, this is an H2, and of course, this one, that means it hydrolyzed this heterocycle, that pyrazine derivative hydrolyzed is Schiff's base, right. Schiff's base, that means hydrolysis would give you this ester here, and on this side it would be basically this would be valine, the other should be this amino group. That means basically hydrolysis would take place in the imine position. So, one side will generate this amino group and the other side will have the ester group. It is nothing but it is a tryptophan derivative, and under the same condition also decellulation takes place. So, it is a nice way of getting these optically active tryptophan derivatives. Okay. And so, what else? One more style of getting indole derivative is well known, that also starts from these alkyne derivatives. So, alkyne derivatives here again something like this, if you have and this NH2 and it is a very popular one. What you have to do, just basically you have to use a base and you will straight away go to the product here with substitution. That means these alkyne derivatives of all of us know can be obtained by Sonogashira coupling from the corresponding iodo compound. So, that means you can make use of the terminal alkyne. So, terminal alkyne, right, that means they are iodoaniline. You can separately do this Sonogashira coupling, and then you can get to this one, and then the cyclization can be achieved by use of different bases. Okay. Like the one example I will tell you, it is quite need to see that how this is alkyne can be converted to corresponding indole derivative. Here you have phenols fluorine substituents, and mind it is a base, sodium methoxide, ethanol, and of course, ethanol is there means the temperature is not very high, only 70 degree centigrade, and once again in one pot you get to the corresponding indole derivative. Okay. And that too 2,3 unsubstituted indole derivative. Okay. So, what you see here that three things are happening. One is cyclization, as if this nitrogen minus is attacking this alkyne. So, undergoing cyclization. The second thing that is going decellulation. Third thing that is taking place is known as alkoxy decarbonylation. That means COOMe. So, this is, or in this case methoxy decarbonylation more precisely, methoxy group and the decarbonylation taking place. So, you get to this one, and okay. Now, this has been known, there are in most cases either ethoxide, sodium ethoxide, potassium ethoxide or potassium tertiary butoxide. Very recently what I said is a Nockel type, it is a Nockel actually, Paul Nockel is a German scientist. What he did, his protocol is very similar, but he could again publish in a good journal, only doing a small change in the reaction conditions. What was it? It is a potassium tertiary butoxide and NMP. What is it? N methyl pyrrolidinone, again heterocyclic, right. So, it is a high boiling solvent. This, and of course, the product is the corresponding indole derivative, So, what is the difference between the previous one and this one? In the previous case, we had sodium ethoxide, ethanol and 70 degree centigrade. In this and the latest one, only you have lowered down the temperature. So, and that means this is a good achievement, just lowering down the temperature, and why it is so? Because what is the job of the NMP? NMP actually solubilize all these alkoxides. Okay, it can help. So ethanol does not dissolve these alkoxides, but here it can solubilize this alkoxide, and hence this you can accelerate the reaction. Okay. So, there are other reactions, I mean there are many other kinds of reactions I have already told you before. There are named like Castro reactions, again starting from these iodo-anilines. Then you have paradigm catalyzed cyclizations of allyl anilines. Then there are other also called Indole synthesis, then Indole synthesis, Indole synthesis. So, likewise many, but the popular one, most popular one what we learned is still there in the textbook though, and that is known as Gassman-Indole synthesis. So, I think you will find this Gassman-Indole synthesis both in Gilchrist books and Jules book, but just very briefly what it is nothing but it again starts from aniline. You start from aniline, and I will just tell you only this much. Okay. You generate something like this amino kind of ketone, and here you will have the way they make this substrate introduces an ASME group at the this particular position. Okay. This is a sort of a kind of, you can say, intramolecular Pomeroy shifting. Okay. I mean I can go on talking about it. It starts from actually something like this, then you do this the corresponding disulfide, the disulfide under condition it forms the sulfonium salt, then undergoes then in the presence of triethylamine it forms carbanion, and just like Somerset-Hauser reaction it undergoes incorporation at the ortho position. Okay. And of course, once you have a substrate like this, and then rest is quite easy, just simply hitting it you will end up in an indole derivative with an ASME group, Of course, and the next one is no, but you have to remove sulfur here. How do you remove sulfur? The standard protocol is Raney-Nickel. So, if you use Raney-Nickel, sulfur is knocked off, and so your product is this. Okay. And the last one is what? Last one is Madelung synthesis. What is Madelung synthesis? Madelung synthesis is again it is something like this, right. You have to have a CH3 group here, NH and this thing. What it does actually you have to use a strong base. So, potassium tertiary butoxide and orthotoluidine can be formilated in the presence of formic acid, and you get the formal derivative N-formyl to orthotoluidine. So, in the presence of strong base, so what you will get? You will get the corresponding indole derivative. Mechanistically what is mechanism? This reaction forms a anion here, NH, and then the CHO. So, that means, and this anion formation is I think we call it in fact a lot of people have called this name, it is called lateral metallation. It is known as lateral metallation. Lateral metallation means basically lateral means sidewise, that means side chain metallation, and more precisely it is the benzylic metallation. Okay. And the latest development in this area, if you use N-butyl lithium, the reaction can be run at 20 degree centigrade, otherwise the reaction has to be carried out at let us say 200 degree centigrade. So, there is a major change now. Okay, and I have a paper with me, the same person known as Bartoli, right. Remember Bartoli indole synthesis? Bartoli in 1990 he has modified the Madelung procedure. He has used dilithium compounds, and instead of using a formyl group he has introduced this ester here, and then converted converted them to corresponding indole derivative. Okay, that is a little more versatile, because you can make use of any kind of ester to introduce the substituent at the 2 position. Okay. So, that means all these, some of the old methods also are still useful, some are still useful, but and among the new methods, which one is which are the new? Let us say, so far we have described 6 or 7 different indole synthesis we talked about, right. Which one is something is more versatile? So, in the last class we talked about 3, right. Fischer, then Bartoli, and then it's Zetsku. Okay. So, in the last class actually Fischer indole is most versatile probably, and the next most versatile could be I think Larock, but it has